sorry, this is a D.
D alpha V. Okay.
Yeah, it's the one defined before, right?
All right.
Where is
Yeah.
it? Somewhere here.
Here. Yeah. D alpha. Okay. Thanks.
So we can forget about this notation now and go back to the symplectic form. Namely, consider this relation here when we rewrite explicitly this beta, just to make things clear. This is 2 to the minus 1 G B G W minus 2 to the minus 1 BW, and just write explicitly what is this alpha, the alpha. This is alpha of B plus W minus alpha of B minus alpha of W. Now, we can observe one thing here. The right-hand side of this equation is symmetric, while the left-hand side is antisymmetric. And that means that this must be 0. And now if we look separately at these two basically two equations, we have the first is that GB GW minus VW is equals to 0. And this implies that G is a symplectic matrix. This notation here is just saying that a symplectic group on FP, and just not writing the F. This is the first relation. The second relation is we have two alpha of B plus W minus alpha of B minus alpha of W is equals to 0. And that means since 2 is invertible, because we are considering fields of out characteristic, that means that alpha is a linear map. So what we get from these two things is that we can identify the group of center fixing automorphism with another group, of course, that is the affine symplectic group. And since these two relations are independent of each other, this group has a semi-direct as a product structure, namely can be written as a symplectic group that is coming, let's say, from the first condition. And then we have the semi-direct product with the basically the phase space, because yes, this is just coming from the second conditions where we have the linear maps in the center fixing automorphism group. So
so we are like 50 minutes into the session, but if you still have time, can you read the last line again, please?
yeah,
I don't want to delay you, but
yeah, sorry, because for some reason I see my pen writing with a lot of delays, so it's harder than usual to write.
yeah,
Yeah,
no,
it's just
otherwise super good.
yeah. This basically means what I was saying is from these two conditions we derived the group of center fixing automorphisms, and this group is basically the symplectic group times the linear maps that we can just write as basically, yeah, in this way, as a point in the phase space. And this group, well, just to give it a name, is the affine symplectic group. So I don't know, I have a little bit more, just stop me if we run out of time. So because now I would talk about the Weyl operators. For the Heisenberg group. And to do that, we first introduce a character of FP. This is just a map into the unitary circle, such that an element X is mapped to e to the 2 pi I over p x, and this is I just write as omega of x to start with Marcus notation. Then we consider the polarization of the discrete phase space, written as Zn plus Xn, where this Zn is basically the span of E1, En, and this is the span of F1, Fn. And then we define these Weyl operators, W of Zx t. These are operators from the Heisenberg group to unitary operators over n qubits. Fu, where this f is just a function on the discrete phase space. Sorry, it's a function on fp to the n. So, like, for example, on the position space, to keep the analogy with the usual case. And this is defined as chi of t plus z dot q plus 2 to the minus 1 z dot x, and then it's acting on f of u plus x. So, okay. Now, these operators, let's say, are reps of the Heisenberg group. Now that also we have that W of Zx is traceless, except for W00. So this is basically just the identity. And if suppose that chi tilde is another character of FP, then that means that if we if we define a W of chi tilde as before, but with chi tilde instead of chi, then this is unitarily inequivalent to W. And last property, that is just the Stone fundament theorem, That is actually the most important one for us.
Mirko, excuse me, what do you mean by unitary inequivalent?
Okay, sorry. That means that in representation theory, when you have two irreducible representations, so basically two homomorphisms of the group, you say that they are unitarily equivalent if there exists a unitary operators that allows you to switch from one representation to the other.
Okay, I see. Otherwise, they're inequivalent.
Inequivalent, yeah, it doesn't
Completely.
exist, this operator.
I see. Thanks.
This Thom-von-Neumann's theorem is about unitarily equivalence of representation, and that says that two E-reps of the Heisenberg group are unitarily equivalent if and only if they agree on the center. And I realized I didn't write the condition for this. This just means that they, yeah, it's like as before. So you on the center they behaves in the same way, so they have basically the same character. The point of the Thom-von-Neumann's theorem is that you can prove both implication. Why this is interesting? It's because the symplectic group, symplectic maps are in the group of automorphisms of the Heisenberg group. And the interesting thing is that if we act with the symplectic group on elements of the Heisenberg group, we obtain another irreducible representation. Namely, what we are doing is this, going from the Weyl operators to Weyl operators composed with a symplectic matrix G, let's say genus P, to make things clear. And this is another representation, but these two representations agree on the center. And so by Thom-von-Neumann's theorem, they are unitarily equivalent. So there exists an operator mu of G that is a unitary operator such that this WG of BT is mu of G W of BT mu G to the -1. And this is for any points in the Heisenberg group. This operator is uniquely determined, and this is another result of Thom-von-Neumann's theorem, up to a phase. So yeah, in representation theory language, that means that this is a projective representation, namely, well, this condition of indetermination up to a phase can also be written in this way. So you have mu of GH as a sum function of G and H, mu of G, mu of H. But yeah, here there is a nice point that is different from the usual case for this representation. Namely, this can be linearized, and that's not the case for other fields. In particular, how you can linearize this? Basically, you can find a function. So let's say mu can be linearized, just to write that. So there is a function k such that you have that mu of sorry, not mu, but c of gh is equals to k of g, k of h, k of gh to the -1. And yeah, just to make things clear, this k is a function from fp, sorry, from the symplectic group in the complex numbers. Yeah, sorry, probably was better. Let's forget about that. And yeah, and if you write another representation of the symplectic group as k of g mu of g, then you will not have these phases coming in a relation that is like this anymore. So your representation will be a faithful representation. But yeah, this is a situation that is occurring only for odd characteristics. Okay, and now in principle, I also have the qubit case. So but yeah, I think we are already over time. I can go on if you want.
All right. So thanks so far. I think maybe in the recording we could still go through it and summarize a little bit, and maybe you could propose some exercises. So this one might be a little bit harder, but on the way you were making some side notes. So maybe you could comment whether making some of the calculations would be useful.
Yeah, I don't know. Well, for the UN case, it's mostly a comment on why everything breaks down at this point, because
but with this we can also start maybe next week.
Okay, sure, yeah.
And then we will have a bit of a recap.
Okay, yeah, it could be also useful for introducing stabilizer then, yeah, sure.
Yeah. So okay, should I finish the recording now, or do you want to still summarize a little bit, or somebody wants to ask some questions, comments?
Well, maybe I can just give a summarize everything, and
yeah
just
okay, thanks.
Because it was quite a lot. Now, so if we forget about motivations, that at the beginning I just motivate why at some point we can plug in the symplectic formalism to describe qubits. That unfortunately I cannot tell you now because I discarded the case of characteristic 2. But we focused on the case of fields, of finite fields of prime dimensions, for which we can introduce the symplectic spaces. And yeah, these are so, and we can give some similar definitions as in, for let's say, continuous symplectic spaces. And we can also introduce a polarization of the space. That means intuitively that we split the space in positions and momentum spaces. And then we talked about the Heisenberg group for fields of characteristic that is not true. We studied its center and its center fixing automorphisms, and we saw that they must satisfy some condition that is written somewhere. I cannot find anymore. Okay, this condition here. This is the form of a center fixing automorphism, and we have seen given these results, how it translates on the level of the Heisenberg group, namely that this G appearing in the center fixing automorphisms must be symplectic maps, while the alpha is just a linear map. So we can write the center fixing automorphism group of the Heisenberg group as a semi-direct product group that is given by the affine symplectic group. And lastly, we introduced representations for the Heisenberg group that is given by Weyl operators. The way to construct them is to introduce a character of the base field and the polarization of the discrete phase space. And yeah, these Weyl operators are given by this condition here. And yeah, I didn't prove that, but it's kind of easy using some character formula that these representations are irreps. And while it's easier to see that these operators are all traceless except for the identity. And then I mentioned the Stone-von Neumann theorem that basically say that two irreps of the Heisenberg group are unitarily equivalent only if they agree on the center. So basically they are associated with the same character in as a little abuse of notation. And by Stone-von Neumann theorem, we saw how to how symplectic maps act on these representations. Since they preserve the center, then we have this relation here. So we have two representations that by Stone-von Neumann theorem are unitarily equivalent. So there must exist a unitary operator that conjugate between each other. And lastly, I commented that one can linearize this representation because Stone-von Neumann theorem holds up to a global phase. So in principle, this operator is defined up to a global phase, but in the case of odd characteristic, one can trivialize this phase and makes this mu a faithful representation of the symplectic group. Yeah.
All right. Thanks, Mirko, for the overview. Okay, I stop now and then we continue next week. Yeah.
Okay.
Thanks.